Good morning everyone, my name is Mercedes and today I'll be presenting my final year project titled The Development of an Instrumented Bed Monitoring System. Hospitals around the world are currently facing a dilemma known as hospital-acquired conditions. This phenomenon is distressing to many inpatients as they are subject to complications that arise during the course of their hospitalization that were previously not present at the time of their admission. Hospital-acquired conditions have been proven to be a subject of concern as affected individuals have a 72% increased risk of mortality, along with an extension of their hospital stay of about 8 days on average. And since most patients spend the majority of their stay in the ward, the hospital bed is without a doubt a major hotspot. With that in mind, an instrumented bed monitoring system was designed to tackle two major hospital-acquired conditions that predominantly occur within close vicinity of the hospital bed: falls and pressure injuries. Falls are the second leading cause of injury within the hospital. It frequently happens when one is trying to get into the bed or out of the bed. On the other hand, pressure injuries, otherwise known as bed sores, affects 2.5 million patients worldwide annually. A skin sore develops when one sleeps in the same position for long periods of time. They often come accompanied with other deadly complications like infections. Both of these hospital-acquired conditions are hard to heal and have devastating effects on one's quality of life, especially for elderly patients. During the initial investigation, it was found that both of these hospital-acquired conditions were hard to heal and thus most hospitals focus on prevention practices. In fact, their prevention practices are structured in a similar way, whereby a bundle of risk assessments, staff protocol, and technological devices were utilized. This can be seen where you have staff performing regular roundings to prevent any unauthorized bed exit that may lead to falls, along with regular repositioning every 2 to 6 hours for pressure injuries. However, there is a key weakness in the current practices, whereby it is dependent on the healthcare professionals to perform regular assessments, regular rounding, and regular repositioning. This makes it limited by the shortage of staff and their adherence performance in the healthcare scene, on top of any lack of training and proper protocol. Hence, this project aims to develop an instrumented bed monitoring system that can provide continuous monitoring of a patient's movement on a bed, mapping out their position, including getting on and getting off the bed. It is hoped that the continuous monitoring nature can help identify when staff intervention is truly needed, freeing up the healthcare workers to work on other matters and reduce their workload. Here is an illustration of the main system components in the instrumented bed monitoring system. A total of 3 PCBs were designed for this project. The main board contains the main microprocessor, ESP32, and communicates with the other two boards through I2C. Each peripheral board contains an I/O extender that reads values from the sensor array. A Nextion touchscreen has been used as the main user interface at the bedside, while a web-based user interface has also been developed. Both perform similar functions and provide continuous monitoring of the bed to the user. A 3D printed casing and backplate meant for the touchscreen, speaker, and main board serves as a bedside console for easy access. The entire console would then be mounted onto the bed headboard as shown in the illustration. As mentioned before, this device has 2 user interfaces, a touchscreen UI at the bedside console and a web-based user interface. On the main page, the left side of our screen shows the real-time monitoring of the bed, updating every second and displaying the new position and movement of the person on the bed. From here, the user can also see the current bed status. An audio notification will be played when the bed becomes vacant or occupied, essentially acting as a bed exit alarm system. This feature is reflected in the web-based UI in real time, allowing it to act as a remote monitoring system for nurses to verify the current status of their patient. A no-movement alarm has also been set up to tackle pressure injuries. Once the bed is occupied, the alarm starts counting down and will eventually ring once the set time period is up, indicating that it is time for the patient to shift and reposition their sleeping posture. On top of that, the algorithm is designed to reset the alarm if any large movements are detected. In this way, when the nurses perform their regular roundings, they can decide to not wake up certain patients and reposition them if the device shows that they have already recently moved by themselves. There is also a call nurse button which triggers a notification on the web-based UI for users to notify the healthcare providers. From the main screen, Pressing down on the settings icon will bring the user to a settings page, where the alarm period, screen brightness, notification volume, and more can be adjusted. On the right side, a dynamic QR linking to the web-based UI can be found. Further network and date time settings can also be accessed through the buttons at the bottom of the screen. The next slide shows a close-up of the web-based user interface and its features, showing the current bed status, bed history, no movement alarm, and more. Moving on, we will discuss the sensor array designed for this device. Although commercial sensors were considered, a self-constructed sensor array was eventually settled upon, due to a number of factors including cost and the sheer number of wires and I/O pins required. This is a qualitative sensor array that provides a signal when two conducting metals touch and current is leaked into the input pin. 0.15 mm stainless steel wires were chosen for its optimal strength, tension, and surface area. These wires were sewn into fabric using a sewing machine, creating a sensor array that resembles a mattress protector. This sensor array consisted of a top piece with 16 horizontal running sensor lines and a bottom piece with 8 vertical lines, making up a total of 128 sensor nodes. Each piece was attached to their respective PCB boards with I/O expanders. The design of this matrix allowed for the usage of only 24 I/O pins in total. This next slide illustrates the placement of the stainless steel wires sewn into each piece. With two loops consisting of 4 running wires for each sensor line, there will be a total of 16 possible touch points for each detection. For this particular project, only a single bed configuration was considered. Here, we see the pictures of the actual prototype. These sensor sheets are stacked on top of the mattress under the bed sheet, much alike a mattress protector. This sensor array was tested to be more than 99% sensitive for items that are more than 350 grams in weight for each sensor node. With the average human hand being about 400 grams in weight, the array is proven to have sufficient sensitivity for detecting human presence. Since the entire array works on the rolling ground principle through the 16 horizontal lines, a 5V source provided to the array would cause each vertical sensor line with a 12K resistor to be 0.4 mA. This means that the maximum current that will be possible in this array occurs when all 8 sensor nodes on a single horizontal line is in contact, coming up to a total of 3.3 mA. Given the low maximum current, combined with the stitching pattern of the stainless steel wires that make them exposed to only one side of the fabric, this makes the sensor array relatively safe for human use. To tackle falls, most experts have agreed that constant monitoring of high-risk patients along with swift treatment is the way to go. Bed exit alarms have shown their effectiveness in the healthcare setting, as they allow staff to know immediately when a patient is making an unauthorized exit. As introduced earlier, this device has its own bed exit alert which defines the current bed status as occupied or vacant. An occupancy threshold of more than 5 contact points was chosen based on the average number of stray points left behind by the previous user. With this threshold, a total of 50 attempts of getting on and 50 attempts of getting off the bed were tested. Through this test, the device has shown to be 100% accurate for getting on and 92% accurate for getting off. Our other objective was on tackling pressure injuries, which currently require regular repositioning by nurses every 2 to 6 hours depending on their protocol. For this device, the alarm is armed once it is considered occupied, continuously counting down to 0 to measure how long this user has been immobile within his particular position. Once the timer reaches 0, the alarm will ring to alert the staff, indicating that it is time for repositioning. However, many people often move unconsciously by themselves. Therefore, the device was programmed to reset the alarm if it detects movement from the user. The final threshold chosen was a change in more than 3 total sensor points, whereby 96% accuracy was achieved for 50 attempts. Furthermore, the full array reproduction accuracy for detecting a human sleeping posture was tested on 6 different sleeping positions. Due to flaws in the original sensor array design, there is some signal leakage through overlapping sensor nodes that causes the results seen to be rectangular. Hence, it can be said that the most prominent error for this device comes in the form of false positives, eventually leading the human shape accuracy to be only 70.3% accurate. In summary, the exact human shape reproduction is relatively low for this device at 70.3%, However, the sensor array is stable and is sufficient to detect human presence and movements, proven by the high accuracy of the alarms and alerts. Although lingering stray points were found, they were not stubborn in nature and easily reset their connection with slight movement exerted onto them. The scanning of the array once per second has also proven to be sufficient for its intended use. All alerts and alarms are also activating as intended. Given that prevention practices are still dependent on nurse protocol, this device can aid in mitigating the hospital-acquired conditions, whereby the nurses can be informed when a patient has roamed off the bed or has been immobile, enabling timely interventions for bed sores and falls.